Clay minerals are hydrous aluminosilicates classified as phyllosilicates. They are characterized by layered structures made of silicon-oxygen tetrahedral sheets and aluminum or magnesium-oxygen octahedral sheets. These layers stack together via weak van der Waals bonds, which allows them to expand or swell and contract. Key groups include kaolinite, smectite, illite, vermiculite, and chlorite. Kaolinite has a 1:1 tetrahedral to octahedral layer ratio. It is non-expansive and has a low cation exchange capacity, typically between 3 and 15 centimoles of charge per kilogram. It forms in highly weathered acidic soils. Smectite, such as montmorillonite, has a 2:1 layer ratio. It has high swelling capacity and a high cation exchange capacity, typically between 80 and 150 centimoles per kilogram. It is prevalent in soils derived from volcanic ash. Illite also has 2:1 layers, but with potassium ions between the sheets. It has a moderate cation exchange capacity, around 20 to 40 centimoles per kilogram, and is common in less weathered sediments. Vermiculite and chlorite have intermediate properties. Chlorite contains a magnesium hydroxide interlayer. Clay minerals form through chemical weathering of primary silicates like feldspars and micas. Key processes include hydrolysis, which is a reaction with water that releases silica and cations such as potassium and sodium, and oxidation or hydration, which breaks down iron and magnesium-rich minerals. The intensity of weathering determines the type of clay. Smectite forms under moderate weathering, for example in basalt terrains, while kaolinite dominates in tropical high-rainfall environments. Clay minerals drive pedogenesis, or soil formation, through several mechanisms. They bind with organic matter to form stable soil aggregates, improving porosity and water retention. Their high cation exchange capacity retains nutrients like calcium, potassium, and ammonium, enhancing soil fertility. Additionally, expansive clays like smectite exhibit shrink-swell behavior, which causes soil cracking and influences aeration and root penetration. Clay translocation defines key soil horizons. Alluviation is the leaching of clay from upper layers, forming the E-horizon in acidic, humid climates. Alluviation is the accumulation of clay in the subsoil, or B-horizon, creating clay-rich argillic horizons. Soil pH and climate dictate clay stability. Kaolinite persists in acidic soils, while smectite favors alkaline conditions. Clay minerals have significant environmental importance. In agriculture, cation exchange capacity governs nutrient availability, and smectite-rich soils require careful irrigation to prevent waterlogging. In engineering, expansive clays can damage foundations, and stabilization techniques include lime addition. For pollution mitigation, the high surface area and cation exchange capacity of clays enable their use in contaminant adsorption, such as for heavy metals. Soil-forming factors, including parent material, climate, organisms, topography, and time, interact to determine clay composition. This is known as Jenny's model. For example, granite weathers to kaolinitic soils, while volcanic ash yields smectitic andisols. This video about clay mineralogy and soil formation is part of our larger Geology for Environmental Science students course. The course is entirely free and has more than 100 subtopics inside it. We're excited for you to try it, and the link is in the description.